let's move on to balance. Again, you covered these in foundation, or at least they were mentioned as a kind of a black box thing that you put between the feeder and the dipole. The syllabus says you need to know the purpose and use of the balun. Well, how do you use them? Well, you stick it between anything that's balanced and anything that's unbalanced, quite frankly. That's usually between coaxial feeder and a dipole. The dipole is a balanced aerial, coax is unbalanced feeder. You put a balun between the two so that you don't get RF flowing back down the coax. And this diagram, which is in the textbook, shows you that the signal comes up the coax inside, as we've said before, and some of it goes down the one leg of the dipole, the other one goes down that leg of the dipole. One's connected to the braid, one's connected to the center. If you didn't have a balun, what you can get is this I3 current, and that means that current's going down the outside of the coax. Now, we don't want that because that can cause radiation. That can cause EMC problems. It can cause your radio to go into all sorts of odd things. If you're using some sort of interface, it can cause that to trip out. So it's generally a bad thing to have current on the outside of the feeder. And a balun is designed to stop that from happening. It makes the current go into the antenna and not come back the other way. You can have a balun between your radio and balanced feeder, because most radios have got an unbalanced coaxial socket. So if you want to feed balanced feeder directly from your transmitter, you need a balun at the other end, not at the antenna end, but at the transmitter end. And some people, between unbalanced feeder and balanced feeder, you put a balun there to separate the two. And a good example is if you've got a G5RV antenna, which is very popular. You've got a length of balanced feeder coming down from the dipole or the doublet. Where the coax joins to that, you should have a balun to make sure you don't get any of that current coming back down into your radio. Now, there are a number of different types of balun, but there's only one in the intermediate syllabus, and it's called a choke balun. The other types are covered in the full syllabus, so if you stick around for the full, you'll get to hear about other types of balun. I won't mention them because you'll probably get confused. So I think if it says balun, they're talking about a choke balun. What is a choke balun? Basically, it's an inductor. You're adding inductance to the outside of the coax. The idea is, and we look at this example here, if that's the dipole at this end, if you've got any current coming down the outside of the coax, if you've got several turns of coax, it makes a coil, and the coil will resist the passive current. It impedes the flow of alternating current. So it's enough to stop the RF from getting any further. In other words, it chokes it off, hence its name, a choke balun. And there are different ways that you can do this. The most simple one is just to have several turns of coax. I don't know if you noticed on the opening slide, there was a picture of a Coke bottle with coax wrapped around it. A very effective way of making a choke balun. The type B that we've got here, you've got a ferrite ring, nice big chunky ferrite ring with the coax being wound around the ferrite ring. A different variation again, a ferrite rod, like you might find inside an old transistor radio, and you just lap the coax around it and off to the antenna. And the final version, which I don't think gets a mention in the textbook, but is very common, is where you have a single piece of coax, but you put several ferrite rings or beads around it. And all of these are designed to add that inductance to the feeder so that the RF current can't get back down from the aerial, and it only goes in the direction you want it to go. Now, usually at this point, somebody says, "Oh, how many turns do you need?" And that's why I put on the slide, this is not an exact science. You've basically got to suck it in the sea. Give it a try. It'll tell you in books 5, 7, 10 turns, whatever. Try it and see what works. And if you find that you haven't got enough, add a few more turns. That's the way to go. How do you know if it's working? Well, you need a thing called a current probe or something like that to measure if the RF current's coming back down. But that's beyond the syllabus. Read the books if you fancy doing that, and you'll find out all about it. Hello.
Yeah, in the new intermediate book, they don't appear to show the diagram with the currents. So previous slide doesn't appear to be in the new book.
Right. Oh well, you got that for free. Those who've got version 2. So,
but there is a picture of a choke balun, which looks like it's RG58 round around waste pipe, and I reckon there's about 20 or 30 turns on that.
Yeah. As I say, depending which book you read, you'll find all sorts of different things. We did have one intermediate student, lives in Keynsham, just between here and Bristol, and he actually spent a happy weekend making a balun with various drain pipes and Coke bottles and experimenting to find out. And I think he ended up with something like 15 turns of coax on a Tesco Coke bottle. He found to be the best. Why it was a Tesco Coke bottle and not a Sainsbury's Coke bottle, I do not know, but it kept him happy anyway, and he was very happy that he eventually got rid of this current that was coming back down his coax. I've put a note on here, which again, it's not in the syllabus, but it's probably worth knowing that a choke balun doesn't have any impedance transformation. It's 50 ohms in and it's 50 ohms out. You do get other baluns that will change the impedance as well as doing this function of keeping the RF currents out. But these are all sort of 50 in, 50 out. They're just basically just a piece of coax with some inductance wrapped around it. Here we go. Right, let's blow your mind now. An isotropic radiator. It seems odd to have something in the syllabus that's a purely theoretical thing. You can never have one of these, although we did have a student a few years ago convinced that he bought one on eBay. And I think that really was somebody with snake oil in the inventory. But it's a theoretical antenna. Sometimes people call it a point source. In other words, it's the size of a pinhead. And it radiates in all directions, not just in terms of like on a map, but literally in a sphere. So I found this picture, which I thought was the best I could illustrate it. Point source antenna in the middle, and it's radiating energy literally at all points of the globe equally. And I've got to stress, this is not a real antenna. You will never get anything like this. But it's a standard that we compare real antennas to. So if you've got a dipole or a Yagi or anything, you can compare it with this theoretical thing to see how well it's performing in terms of its gain or its angle of radiation or whatever factor you want to compare. Now, when you do that comparison, any gain is expressed as dBi. So it's decibels, like we've come across before, 3 decibels, doubling the power, etc. We've got a little I after it. And that I is the isotropic comparison, okay? So if you've got your RF power from your transmitter multiplied by the dB gain, and it's a little I, it becomes the effective isotropic radiated power, EIRP. There's only one band in the license that uses that, as I'm aware of, and that's 5 megahertz. And as intermediate users, you'll not be allowed to use it. So I'm not quite sure why it's important you know about that. But anyway, it's in the syllabus, so I've told you about it. If you see that, it's got the I in it, it means isotropic, and it's being compared with something that radiates equally in all directions. To try and put some flesh on that bone, this is the radiation pattern from a dipole in 3D. Okay, we talked before about it being a 3D thing. You can just about make out in this, there's the dipole running through the middle. You can see that figure of 8 that we talked about earlier. There, see them in sort of cross section. So the maximum radiation is up and down, nothing off the ends, they call it a null. I've tilted it this way so that you can see the equivalent horizontal pattern, if you like. So we've got the same RF power that we had before, but rather than it being from that point source, it's actually coming from this dipole. So it's taken that sphere and it squished the ends in, if you like. If you've got a round balloon, if you ever do this, you've got kids or whatever, you've got a balloon and you push the ends in, the middle bit squishes out, doesn't it? You end up with this sort of a donut-shaped balloon. And what it does, it pushes that power or the balloon out that way, and it squidges it in that way. So the same amount of energy, the 50 watts that you put into the antenna, is being used, but it's squirting most of it in that direction and none of it in that direction. The comparison with the sphere is that in the maximum direction, that bit, it has 2.15 dBi gain. So if you see anybody talking about a dipole having a gain, that's what they're talking about. Compared with the sphere, the isotropic radiator, it's got a gain of 2.15. But on the grounds you can never have an isotropic radiator, it's a bit of a pointless comparison, to be honest. So quite often, or more often, people use the dipole as the standard because it's the basic antenna for radio. And then they use this, dBd. Okay, so if you're comparing your Yagi with a dipole, the gain it has could be, compared in dBd. Some unscrupulous antenna manufacturers will just say dB gain. And if they don't quote it, the chances are they're using dBi because it adds 2.15 to whatever figure you would get otherwise. So if you see something it doesn't specify it, be suspicious. But dBd compared with a dipole, dBi compared with an isotropic radiator. And if we're comparing it with a dipole, we generally just use ERP. So it doesn't say effective dipole radiated power, it just says effective radiated power. That normally means a comparison with a dipole. Depends who's writing the article, but there we go. That's the comparison between dBi and dBd. Talked last week about various antenna concepts, and we've covered some of them there in that little discussion. But there's a couple that we didn't cover, and they specifically relate to Yagi antennas. So you may remember from last week, we looked at these diagrams last week, which we were looking at that point about gain in terms of being more going forward than back or in the round for an isotropic source. And the fact that if you look sideways, it kind of tilted upwards a little bit. It wasn't flat onto the ground. So that still applies. We're not changing anything, but there's another concept that is in the syllabus, and it's this thing called front to back ratio. And what that tries to do is express how well it throws the power forward, because it could be that you've got great gain in the forward direction, but you might have good gain in the backward direction as well, in which case the ratio wouldn't be very good. It would be, well, it could be zero. If you think about a dipole, it radiates equally in two directions. The front to back ratio of a dipole would be zero because the gain is the same in both directions. So we've got this thing called the front to back ratio, and the example that's shown on here, you can see from this chart that the forward gain is about 8, somewhere between 7 and 10. We're going to use 8 as a number to work with. And then at the back end, it's actually these rings go the other way. So that's a -10 ring, that one, and then that's a -5. So we've said for ease of reckoning, it's about -6. So you've got 8 decibels forward and -6 that way because it's going in the opposite direction. And you take the -6 away from the 8, so you actually add them together. So what that means is that the front to back ratio is 14 decibels. In other words, there's 14 dB more energy going that way than there is that way. It's one of those things. It doesn't actually mean a great deal, but if you're comparing two antennas, it can be quite useful to see. Some antennas are tuned for best forward gain. Some are tuned for best front to back ratio. If you've got a high front to back ratio, what that means is you can turn your beam and stations in this direction will just disappear. You won't be able to hear them. And that can be quite important in contests, that if you've got very strong stations in one direction, if you can turn your beam away from them, they literally disappear because they're in this sort of null section here, perhaps. So the higher the front to back ratio, the more that effect will be seen, and the more power you effectively you're chucking forward. And the lower the figure, it probably means it's radiating equally in two directions. Okay, so not much else to say about that other than that's what it is, and that's how it's calculated. There's nothing in the syllabus to say you have to calculate it, just to be aware that it is a comparison of the forward and the backward gain, that's all. Might mean a bit more in a minute when I come back to it.
Steve, sorry to interrupt
Yeah.
there. Your front to back ratio is in decibels. Is that right, or should it be decibel dBi?
No, the front to back ratio is always in decibels because we're comparing dBi and dBi. The comparison is then just dB because it's the difference between the two, or the comparison between the two. So it likewise, if you're comparing, say, a voltage against 1 volt, then it would be dB volts. But if you're comparing two voltages, it would just be dB, because they're the same unit, if you like. Sort of the thing cancels itself out. Does that make sense?
Yep, great, thank you.
But well spotted. Now we covered this last week, but again, the syllabus for some reason mentions it twice. It must be like New York; it's so good, we'll use it twice. But in relation to a Yagi, it means exactly the same as we talked about last week. That angle between the maximum angle of radiation from the antenna and the horizontal ground, that angle is the angle of radiation. And again, ideally, you want that to be as low as possible, so you get the best DX, and somewhere almost horizontal, 5 degrees or something is said to be optimal. But there's not many antennas you can get that low. But that's it. It applies to a Yagi just in the same way as any other antenna. That's the point I was making. Now, this one is, again, specifically to the Yagi, and it talks about the beam width. And we've used before comparisons down to the half power point, or a 3 decibel reduction. And this is applied to the antenna, to the Yagi, in its radiation pattern. So I've marked on this one where the 3 dB mark is roughly. And that's the beam width of this antenna. So it's about 60 degrees. And in the sideways elevation, again, there's the difference to the 3 dB point is about 45 degrees. And you can imagine if you can get that beam width narrower, you will get a better focus. It's a bit like focusing a torch, you get a brighter beam. So if you can get that, if you're comparing two antennas particularly, and one's got a beam width of 25 degrees and the other 60, the 25 degrees will be sharper and probably have more gain. The syllabus requires you to know that it's the 3 dB point. So I guess they could give you a diagram like that and say, what's the beam width of this antenna? And you'd have to read off where the 3 dB point is, work out the angle. I haven't seen any questions like that, but you never know. I'm racking my brains to think, other than the definition, what could they ask you? And that's probably about it. They might say, what would you call the angle between 3 dB points, and it's the beam width. Or they could say, what is the beam width definition, and then give you 3 or 4 possible answers. So let's move on to EMC then. Huge topic and quite a complex topic, but the bits that are in the syllabus, I think, are fairly straightforward, but you'll tell me if not, and please scream if I've lost you at any point. So the key concepts, the first of all, is that any electronic equipment can transmit and receive. And I think that's something that people found very odd. A little while ago, there was a story about a television in Wales blotting out the broadband in a village. And I heard somebody on the radio saying, well, how can a TV do that? It receives pictures, it doesn't transmit, but any bit of electronic equipment can emit radio frequency energy. Likewise, any bit of electronic equipment can receive RF energy. It may not be designed to do that, but it will, because it's got electronic circuits and they're capable of doing that. So in the ideal world, all this electronic equipment should be able to coexist without interfering with each other, causing any problems. So, you know, taking it to the extreme, you know, your fridge and your iron can work in the same room without any hassle because they don't cause each other any problems. But when you get to things like microwave ovens or indeed computers, which can generate RF, they have to be made so that they're compatible with each other. So I've tried to stress it on the slide. From an electromagnetic point of view, they have to be compatible, and that's where EMC comes from, electromagnetic compatibility. That may be very basic, but you'd be surprised the number of people that just see the letters EMC and they don't actually get where it comes from. And we've talked previously about there being electric fields and magnetic fields. So again, it kind of all starts to gel together, doesn't it? That they have to be compatible with each other. Now, any new equipment that is placed on the market has to meet British Standard Institute standards. They've got a whole raft of things for electromagnetic compatibility. And if you're going to build something and sell it on the market, you have to get it type tested and get a certificate to say that it's, you know, it meets the standards. And if it does, then it's said to have good immunity. In other words, it's immune from interference up to a point. Now, you can take the best equipment in the world. If you install it in a rubbish way, then it may operate outside of those standards, because the standards are done in laboratory conditions. You know, everything's perfect. All the cables are nicely tied off, and you know, it's working in ideal conditions. In the real world, it may not be quite like that, especially if, and I'm not casting any aspersions, but some DIY installations leave a lot to be desired. So you might find that a perfectly good bit of equipment doesn't operate as it should do, and then it's said to have poor immunity. In other words, it's not immune from picking up interference or indeed emitting interference. And the last point, which again is in the syllabus, older equipment may not even know there was a standard when it was built. You know, if you've got something like a valve radio from 1942 or something like that, it's very unlikely to meet the current EMC standards. So again, it will have poor immunity. And there were certainly certain types of radios that were as good transmitters as they were receivers, and could cause all sorts of problems in a neighborhood if somebody was operating incorrectly. So this is not a new problem. It's been around for a long time. Just there are standards for it now, and we have to meet them. So we are dealing with amateur radio equipment, which deliberately generates high radio frequency fields. You know, we couldn't transmit around the world if we didn't generate lots of RF. So the usual EMC rules don't really apply, because you can't type test a transmitter to make sure it doesn't transmit, because that's what it's there to do. So there's an onus on us as the owners of the transmitters to know a bit more than Joe and Josephine average, and we need to know how to deal with issues when they crop up, and we may need to take special measures to improve immunity. In other words, make things better than they would be otherwise. And I've lifted this straight out of the syllabus because it says immunity can be improved by screening and or filtering power, signal and control leads. Now we're going to look in a bit more detail what that means, but some of the examples are quite illustrative in bringing that home. And initially this looks like coax, but what you've got here is a multi-cord cable with a screen like you would have in coaxial cable, but you haven't got the one core, you've got several cores. So this is screened cable, and that's very good at keeping RF out of these inner cores because it bounces off the outer core. So that's quite a good example of screening. These metal boxes here are RF screens inside some computing device, because I don't know what's inside them, but the whatever it is, they want to keep it clear of any RF interference. So this again, screening in action. And then in terms of the leads, I've got a couple of examples. These two here are television interference filters. So you'd find those in the signal lead of a domestic television. They're both high-pass filters, just as an example, but we'll come back to that in a little while. We were talking earlier about things not changing. This diagram here over on the left-hand side was in the RAE manual that I studied some 40 years ago, and I don't know if it goes back much further than that, but I thought it was just a theory thing. I had a problem with television interference. I built one of those and the problem went away. So it really did work, and I think every bit as effective now as it would have been all those time ago. So again, you can see the construction here. It's not very technical, but setting it up can be a bit tricky with this one because of the frequency dependent tuned circuits here, but certainly not beyond the wit of man to build such a thing. You can buy them. And this one over on the right-hand side is a mains filter, which or sort of a pre-packaged thing that contains all the necessary gubbins to filter a power lead. So these things are readily available. They're not sort of mythical beasts or anything like that. It doesn't take long to find them if you go looking. We're going to look at each of those in a little bit more detail. But I thought that would just be as a nice introduction of what that syllabus point is driving at. So, effects on digital audio broadcasting and digital TV. Very similar, but one's sound obviously and one's vision. A bit like the FM that I mentioned earlier, it tends to be either a problem or not. The beauty of digital systems is they're very tolerant of interference, but when it goes, it goes. And the picture I've got here, I managed to find this on the internet today, of a pixelated TV picture. You can see that it just bits missing and bits of it's frozen. Usually that's accompanied by a complete loss of sound, and you quite often see this on outside broadcasts on the television when somebody goes and stands in front of the antenna or something and the signal goes, or on Formula One racing, if they go around a blind corner and the picture disappears or the sound goes. So yeah, not a lot to say about that. Just pixelation and loss of sound are the two main symptoms that there's a problem with digital broadcast equipment. EMC isn't just at home. It applies equally in vehicles. I've put and vessels because that's not in the syllabus, but it does apply to boats as well, on inland waterways for intermediate purposes. But if you go over 10 watts, then you can have problems. And why 10 watts? Well, that's the point at which car manufacturers say you shouldn't operate in a car. Covers their backside very well. But if you put a transmitter in your car that's over 10 watts, you might find that you've made your insurance void. So be aware of that. And if you're going to put a 50-watt transmitter in, you may have to tell your car insurers. Chances are they'll say it's fine, but if you don't tell them and there's a problem, then I think they'll probably find that as a way of wriggling out of paying any claims. What problems can it cause? Well, basically any electronic system in the car can be affected. So we've got the audio systems, sat-nav, remote lock-in, security alarms, fuel management. The remote lock-in one, I can't remember whether it was BMW or Mercedes. It was a high-end car that decided to put their key fobs on 70 centimeters and got very embarrassed when radio amateurs driving past on 77s were causing the locks to operate on the car, or in one case caused it to lock some children in a supermarket car park, and they couldn't unlock it with the key fob because somebody a few cars away was rabbiting away on 77s, and that brought it to the fore, and they wanted radio amateurs hung, drawn and quartered, when actually it was the car company's fault for putting their locking devices on the same frequency that amateurs use. So they all had to be modified. So it was a bit embarrassing for the car company, but it brought very clearly this problem about compatibility. If you use the same frequency, then don't be surprised if you get interference. Clearly, the last one, fuel management, can have a massive safety issue. If you're driving along at 70 miles an hour and you key up the radio and it stops fuel going to the engine, that's not a good place to be. So this is one of the reasons that the car manufacturers say keep your radios down to 10 watts if you're using them mobile. So how does it get into the electronic systems? Well, usually people run RF cables next to control units, or indeed along the wiring loom of the car, the DC supplies. And a bit like David's example of the telephone wires, they act as an antenna and they pick up the RF, put it into the electronic units, who have got semiconductors, they rectify it, turn it into a voltage and do whatever they're not supposed to do. So yeah, it's not just an inconvenience of the sat nav not working. It could be that your engine stops working, and that can have serious implications. So EMC in vehicles is not a trivial matter.